So in this video, we're going to talk about geometric series. And it's important to remember the vocabulary for series is that series is a sum of a sequence between two identified terms. It could just be between terms 1 and 2. It could be, as you saw earlier, the sum of A1 through A5. So the difference is, with geometric, we might see something where we're multiplying by 3 for each term. And what happens is as I keep going, we continue to get larger numbers, and those larger numbers would then be all added together. So the sum of these 5 terms would be, instead of just put a comma here, we would add them all up. And as you can see, that can get kind of, even with this simple one where I took 2 and multiplied it times 3 and then by 3, by 3, by 3, you start to get pretty large numbers, and that's why we have formulas. So S of n is the formula used to add all these terms together. And it's also known as the final sum. So it's the formula, but it also represents the final sum of the formula. Remember, n in math means last. So there's also this Greek letter sigma, which can be used with geometric series. It's the universal letter used for math and summation. So that letter is just a way to basically tell people to add up an equation inside. There is, of course, an an in here, which is the formula in this case for geometric. It could be arithmetic. And we start at whatever term. The basic formula starts at 1 and then goes to n. But, this could be 3 to 7, as we learned when we did the arithmetic problem. Same thing with geometric. So the geometric equations, the first one is for something called a finite sum. Finite means it ends. It has an ending value, which is interesting. So this one will say we're going to add a distinct amount, like S of 10 or S of 20 or even S of 1,000. Well, in geometric, because of that convergent, non-convergent, there's actually a second formula that we'll talk about that's for infinite sums. So if you have a finite sum, the formula is take A1 and multiply this ratio of 1 minus r to the n. Notice it's not n minus 1. It's 1 minus r to the n divided by 1 minus r. This does not simplify. You cannot cancel this because this is actually an n number of these. So that wouldn't work because we don't know how many there are. That would only cancel, of course, if it was to the first power, which, why would you do that? That's just one term. So don't cancel or reduce this, just plug numbers into it. A couple of important notes. There's no an in this formula. Remember, when we did arithmetic, both formulas had an's. So there's no need to know the final term to find the final sum, which is incredibly interesting. There's only one formula. Finite sums have one formula. There is a hidden parentheses around the numerator and denominator, so it's very important to understand, especially when you're typing this into calculators, that there's actually a parentheses here and down here, which we learned when we did rational functions. Very important for when you type things into calculators. The r also has a hidden parentheses if it's negative or a fraction that's really going to matter. So we really need to make sure we also encapsulate this in a parentheses. If it's ever something that isn't just an integer. If it's 5, you're good. A positive integer, you're fine. But if it's negative 5, you're going to have to put this into parentheses, or else the calculator will interpret those two negatives as a positive, and r is not, right? If we said it's negative 5. Also, you need to put it in parentheses if there is a fraction. All right, so as I mentioned a second ago, there's another formula for infinite sum. And as you've seen this previously, this is the terminology for convergent, right? Otherwise known as a sequence that has, if we're talking about exponential, it would be a decay sequence. So if it's convergent, we have a new formula. And it's actually the same as this formula up here. But what's happened is that in a convergent sequence, this part will go to 0. It'll go to 0. Leaving you with 1 over r minus 1, and 1 times a1 is this formula. So they're actually the same formula with one term eliminated. We'll talk more about why that goes to 0 when we look at problems that involve the infinite sum. So note, this formula is the same formula as the finite sum. As n goes to infinity, rn goes to 0. There is a hidden parentheses again, but it's, it is around this and around this. Why is it important? Well, we obviously understand why we need to simplify this, but you might think, well, what if that's just a number? Well, if r is between 0 and 1, that's always a fraction. And that's why it's important to remember that there's actually a parentheses there. And the R also can have a parentheses as well, because what if it's a fraction? So remember that we're dealing with things that are between 0 and 1. A1 could be a fraction, could be an integer. Even when it is an integer, you need to turn it into a fraction because R will always be a fraction. So just be careful. Understand that there are two formulas. They're actually the same formula if I cancel this out. And it's just very important to remember those things. But when we actually do these problems, they're actually, in my opinion, a little simpler than arithmetic because we just rely on the calculator to do this very complicated parentheses. Just be careful of where you put all of your parentheses. So in these first examples, we're going to take a look at geometric series equations and sigma notation. So the first thing it says is to rewrite this series that you have into sigma notation. So we're going to start by writing a sigma. In this sequence that is a series because we added an addition sign as opposed to a parenthesis, a comma, starts at A1 and goes up to A5. So the reason that's important is that's the first thing you put on. Those are called indices on sigma. It starts at the first term and it ends at the fifth term. This is what's known as a finite series because it ends. Finite meaning there's a determined amount of values you're adding together. So inside of here, we're going to put an, and the equation for an, as you learned in our geometric sequence problems, is a1 times r to the n minus 1. So to find r, as we've learned before, r is a2 divided by a1. You just take the second term and divide by the first, or any two adjacent terms, right, as we learned earlier. So that will be -3. And so the formula that we have is an is equal to 6 times -3 to the n minus 1. Just continue to remember that this doesn't reduce. There is no common base. There is no common exponent. So that's what goes right here. And that will yield the first part of this answer, which is to rewrite this series in sigma notation, meaning this sigma notation right here will produce, right? This will produce this. If I put 1 in here, I get 6. If I put 2 in there, I get -18, and so on. And then it asks me to evaluate this series, this one and this one, using the formula. So the formula for geometric series is S of n for finite terms is equal to a1, 1 minus r to the n divided by 1 minus r. And so I'm now just going to plug those in, and they actually come from this right here. I mean, you could have found them from up here, and that's one of the reasons the sigma notation is so useful. My a1 is 6, my r is -3. So S of 5, right, there are 5 terms being added up, would be 6 times 1 minus, in parentheses, -3 to the n. The n is the number of terms you're adding, which is 5 terms, divided by 1 minus parentheses r, which is -3. Please make sure you add these parentheses. If you don't, the negatives will cancel, but you can't combine that base with the negative because it doesn't have the same exponent. You've got to be careful. Now on the bottom, before we put this in the calculator, the bottom can't combine. So if you want to say 6 times 1, do not drop that parentheses off right there. All right. And if you want to go ahead and use the denominator's parentheses, remember there's actually a parentheses here and here. If you want to go ahead and use that parentheses and say, okay, well, that's 4, that will actually help you type it in. All right, so using our calculator, what we're going to do is we're going to type that in, but you just have to be careful with it. So 6, open a parentheses, and then we have 1 minus parentheses -3, close parentheses, and then you want to make sure you're outside of here and raise just that to the 5th power. Now, this next step on a calculator like Desmos is important. You want to highlight the whole thing and then say divide. Okay. Also important on a calculator, certain calculators like TIs and Casios have fraction mode. You'd want to put it into fraction mode. So 1 minus, just make sure it looks exactly the same. It's one of the things I love about Desmos is you can see it. And so S of 5, adding these 5 terms up, is 366. So, just to make sure you understand what that formula did, if you were to actually just add those terms together, watch. If I went back to this original equation here, this original sequence here, is at 6 plus negative 18 plus 54 plus negative 162 plus 486. Notice it's the exact same thing as that formula gives you. Now, why is it important? Obviously you can add these things up, but you could add those things up in Algebra 1. So using this formula, which is based on exponential equations, is very important to learn how to use. And what if we had to add up 75 of them? There's no way you'd want to type that in. All right. So the next one is, well, what happens if somebody gives you sigma? Well, now that you know how sigma works, it's pretty easy to be able to use the equation that we have, which is S of n is equal to A1 times 1 minus r to the n over 1 minus r. I always write down my formulas, that way I remember them. So in this case, they're adding up 12. And remember, the reason it's 12, it looks like it's 12. The reason it's 12 is if we take this number, 12 minus 1, we actually get 11. And remember, as I mentioned in my arithmetic videos, the reason it actually is 12 is you always add back 1 to represent the first term. So that's why there's actually 12 things. Now, in that problem, it's kind of a moot point, but over here, it really matters because this is actually 13 terms, which we'll talk about in just a minute. So what we get here, A1 is always this value. This is A1. So what's beautiful about geometric is the values are just right in front of you. So you have a 7 here, all right? And then here, what we're going to do is we're going to have 1 minus r. R is this value. Again, we need another parentheses. Those negatives do not cancel because this is being raised to the 12th power, right? So you can't combine those numbers because they don't have the same exponent. But then we have 1 minus negative 2 here. And so S of 12 is going to become 7 times, again, if you want to, I just think it helps to type it into the calculator. You don't have to do this, but if you want to go ahead and say that bottom is 3, you don't have to. I'll show you both ways on the calculator, but it does help you to just type less. So then you would have this, and this number is going to be enormous because anything to the 12th power is big. So let's see what we get. Clear this one out. Okay, so we're going to do 7, open a parentheses, 1 minus parentheses, negative 2 parentheses to the 12th power. And we're going to highlight this whole thing and then say divide, and then divide by 3. Now again, if you would rather just say, okay, 1 minus negative 2, you do get the same thing, obviously, so it's up to you. Now, the reason this wasn't enormous is because we have a negative r value, which is making one thing positive and one thing negative, one thing positive, one thing negative. So it's actually adding while it's subtracting. But if that was a positive r value, that would be very, very large. So S of 12 is negative 9,000. Negative 9,555. So just keep in mind, when you look at a problem, it's kind of fun to try to figure out why that number wasn't big, and it's because it's alternating between large and small values. Okay, so when I look at this problem is actually, it's fine, it's written in sigma notation, but it's actually sort of a little bit changed in terms of what you see. And there are two things going on here that are, and this is different, very different than when you look at a problem from arithmetic. So what happens here is that these two numbers, as we already learned, they're actually not 12. That's one thing you need to watch out for. But probably more important is to realize that they actually messed with this. And so what we have to do is we have to rewrite the sigma notation. We have to take this sigma notation right here, and we have to rewrite it. First of all, so that it says n equals 1, okay? And then second of all, so that this thing, it has to say n minus 1. So the way we do that is we just write out, we enumerate, we iterate about maybe 3 terms of this sequence. And we determine, well, what should A1 actually be if it were written correctly with the right format? So to do that, you just put 1 into here, right? So it's not complicated, it just makes you stop and pause. So 6 to the 1/3 raised to the, right, we have n plus 2, that would be raised to the 3rd power. We end up with, remember the little toggle here, we end up with 2/9, okay? And then what we do now is we find a couple more terms. So the next one would be 2 plus 2 or 4. So that's 2/27. And then the next one right here, and you only need 2, but it's just always good to have the third one for good measure. That one would be 2 plus 3, so to the 5th power. And oops, make sure you got to be careful. See how that went down like that? You want to make sure it goes back up and put a 5 there. That's 2/81. So what you realize in these problems is that your A1 is actually 2/9. So you're going to want to put that inside the sigma notation. And then your R value, luckily, never changes, which is really cool. The R value, you're multiplying by a third still, and that's why it's important to see what's happening, right? So 1/3 is still what we're multiplying between these, and if you wanted to check it by dividing A2 divided by A1, I'll show that to you. So let's go back and check on Desmos. All right, so if I go in here and say, okay, do I have the right values, right? What I would do is I would take A2, 2/27, make sure you highlight the whole thing, then divide by 2/9, and you can see that that is in fact 1/3. So the R value doesn't change, but it changes A1. And a lot of students look at this and they're like, what did you just do? I actually produced the same exact sequence, but I set it back to A1 so that this would be correct, right? The problem that we had was that this was wrong. So now this is now valid. It's set up. Remember, formulas are written for a certain terminology. And if I change that terminology, it actually changes the formula. And I don't want to rewrite the formula. I want to rewrite the problem. So again, if you were to put in, just to prove to you that that's the case, if I were to put in 2/9, right, and then I put in a 1/3 here, and then I put in its exponent in -1, if I want to find A1, that would be raised to the 0. Look, it's producing 2/9. If I want to put a 2 in there, it would be 2 minus 1, right? So that would just be to the first, as you can see, 2/27. And if I want to put 3 in there, that'd be 3 minus 1 or 2, and you can see I get 2/81. So it is producing the same numbers, which is doing it in a way that the formula will work correctly. And then we have our other thing that I mentioned earlier, which is we do have to balance this out correctly. So that is really 12 minus 0, which is 12, and then we always add in the first term. So that's actually 13 terms that this was originally adding together. So just remember that if this exponent is wrong, you have to fix it. And then you have to rebalance the equation to make sure it works with the correct number of terms that the original problem had. So now I can actually do the problem that was asked, which is to evaluate this. So S of n is equal to A1, 1 minus r to the n over 1 minus r. And S of 13, right? S of 13 is equal to 2/9 now, 1 minus r, which is a third, and it's a third in both problems. That's the only thing that stayed the same. Raised to the 12th power divided by 1 minus a third. So here's the thing, and I just want you to listen to this very carefully because students will always ask, why do we have to do that? We had to do that or we would have had to change this formula. And it's much harder to change a formula than it is to change a numerical value in a question. All right, so now I'm just going to type this in. So just be careful how you do it. 2/9. Nice thing about something like Desmos, again, is it shows you what it actually is thinking you're meaning, which is very convenient. So 1 minus parentheses 1/3. And then we're going to raise that. Click right in between those parentheses, raise that to the 12th power. And then we're going to highlight the whole thing and then divide that by 1 minus 1/3. Okay, and it comes out to this crazy answer, right? And so we're just going to keep it as, we'll just go to 3 decimal places maybe. Just if you want to write out more, that's fine. So it would be 0.33333. Why don't we go to this 2 here so you realize it's not a third. So 33333. So there's 5 3's and then a 2. So S to the S13, the 13 terms added up are 0.33333. And just to make sure you realize it's not a third, I'll put a 2 there, and then of course it keeps going. Again, if you wanted to write down the actual answer, I mean, it's kind of obnoxious, but you would just toggle that, and that would be the actual answer. So in these problems, we're going to continue to look at the formula. S of n is equal to A1 times 1 minus r to the n over 1 minus r. And difference is, instead of being given the information in a sigma notation, we have to get the information from reading the question carefully, as the directions say. So the first thing I noticed when I look at this is they gave us how many terms we're looking for right there in that subscript. They also, of course, gave us a 1, and we're going to find r by determining what is being multiplied between these terms. And you can tell that we're multiplying by 4 pretty easily. Or if you need to, you can always do a2 divided by a1. Okay, and so in this case, that would be 12 divided by 3. Or any adjacent term that you have, you could have done 48 divided by 12. Just make sure that you do the second one divided by the first one. If you do it the wrong way, it will be upside down. So now we just have to fill in the information into this formula. S of 15 is equal to 3 times 1 minus 4 raised to the 15th. That's going to be big. Divided by 1 minus 4 in parentheses. Make sure your r's are in parentheses. And then, if you want to, if you're using a calculator, a handheld calculator, like a TI or a Casio, it might be a good idea on the bottom to reduce that, because remember, the top and the bottom are actually, they're separated by a parentheses. There's actually a parentheses on the top here and one on the bottom. So if you want to evaluate the bottom separately, you can. And I would only say that if you're doing something handheld on a calculator. So if you have Desmos, right, what you're going to do is you're just going to type the whole thing in. Do not try to reduce this at all. You will cause yourself to make a mistake. And you won't even know it because the calculator's doing it, right? So just type it in. And when you type it in, make sure you highlight the whole thing before you hit the division button. Okay, and then you type in 1 minus 4, and we get an answer that is in the scientific notation. Now that answer in scientific notation is perfectly fine, right? So S of 15 is equal to 1.074 times 10 to the 9th power. And, you know, just keep in mind to round to the 3rd decimal place. Keep in mind if you needed to use this to actually calculate additional things, then you would have to use more than 3 decimal places, because the AP and the SAT need you to have 3 correct decimal places in your answer. So if you lop that off in the calculation beforehand, you're not going to have that decimal place correct at the end of the problem. All right, so let's take a look at the next one. Same idea, we're just going to, looks very similar actually. Let's see what we have. So we're going to use the same formula. And it's just a good idea to write that formula down for each problem to help organize your information, but also help you remember it. And then once you have that, we're going to take a look at what we have. Well, we have this. We can find r pretty easily, right? So r is these ones. Now, probably need to break out a calculator for that, because r would be a2 over a1. And in that case, we have some pretty large numbers. So let's take a look at what that reduces to. Don't be afraid of those numbers, because, you know, calculators can reduce them, and sometimes when you reduce it, it reduces it to a very nice number. So let's see what we get here. So 384 divided by 768. Oh, that's just a half, which is very convenient, right? It just comes out to a half. So I know a1, I know a half, but I don't know how many terms there are, right? So sometimes you figure that out after you start to plug things in. Sometimes the formula, this is why I say to always write it down, will sort of help you figure this out. So if I were doing this, I would get to right here and I would say, oh man, that's the problem, right? The problem is I don't know what this is right now. So what I'm going to do is I'm going to just take another little, kind of like I did with R, I'm going to take another little algebra break over here. And since I'm trying to determine the number of terms, when I say the word terms, I need to think about the sequence equation. And you can never really get away from your sequence equations, because sequences are what make up the series, right? So this equation for sequence, the geometric sequence, is the formula that produced the numbers that we're adding. So it makes sense that you would always be needing this if something's missing. So AN means formula or any term, but in this case specifically it means last term, which is the other meaning of AN. So I'm going to put that right here. A1 is 768, and then R is a half, found that a couple minutes ago, and then we're going to do N minus 1. So now we're solving this as if this N were an X, and so when we say solving, you should always write this down if you're lost or you just don't know what your next step is. Always write the order of operations down. And when you solve, start at the bottom. This does not have an addition or subtraction because of the fact that, yeah, there's one up here, but there's actually a parentheses around that. So there's nothing below the exponent that has addition or subtraction, so that's don't have to do it. So I move to the multiplication division step, and I'm going to divide this. And this is exactly like solving an exponential problem from the earlier chapter. All right, that's another complicated looking fraction, so let's take a look at what that is. 3 divided by 768 is something nutty. Let's see what it is. Oh, it's 1 over 256. Now, you may say that's not very nice, but number one, you don't want to write that decimal down, right? You don't want to be doing these problems and writing down that number. You want to write down this, and the reason is there's actually a relationship between 1/2 and n minus 1, and that relationship is the next step, right? So we did this step, and now we need to get rid of the exponential base by using a logarithm. And so to do that, we would log base 1/2, which would cancel this base. And if I log base 1/2 over here, I'm actually going to just do what we did previously, which is say, what do I raise 1/2 to get 1 over 256? Now you can ignore those numerators because they're the same. So the problem really boils down to, what do I raise 2 to get 256, which is actually 8. So this thing doesn't cancel, it evaluates to 8. Now, if you need to use a calculator for that, you could, is it 2 to the 7th? No. Is it 2 to the 6th? No. Right, so let me type that in correctly. 2 to the 6th? No. Is it 2 to the 8th? So you can get it that way. But there's also this other aspect of logarithms that is important. Now, some people, like if you have a TI, there's actually a log base button found under math. Some of the newer Casios have a log base button, but you don't actually need it. Eventually, there probably will be a log base button in Desmos found under function. Currently, there's just log and ln. But you actually don't need a change of base. I mean, you don't need a base button because you have the change of base theorem. And the way that works is you would just type in log or use your log button, and you would type in what you're evaluating. So log of 1 over 256. Now keep in mind, that's log base 10 of that, so it's a decimal. But if you divide this by log of the base you need, you're using, which is 1/2, it'll give you the value. Look, 8. Just keep that in mind if you're ever having trouble with it. So then to finish it up, we're at the grouping symbol. So we need to add 1 to both sides, and we get that n is 9. Now remember, in the world of series, this number has to be a positive integer value. Has to. Just let you know, because n is a number of terms, so it has to be a nice integer positive value. All right, so now I can type that into the calculator. Now that I know what it is, I just take that and put that back in there. And now I can finally come into the calculator and type the whole thing in. So let's see, 768 times 1 minus, this is where that parentheses on that fraction is so important, and you must make sure you click in between those to get this to the right exponent. Highlight the whole thing, then hit divide, which, remember I was on functions, I have to go back to main. And then I type in 1 minus 1/2. And the beautiful thing about Desmos is I can actually see, did I type in what I have on my paper? And that comes out to 1,533. And it's always good to just, once you have the answer, to go back and make sure you say, oh, that's S of 9. And of course, that 9 was found over here. So again, using a calculator like Desmos sure does make your life easier when trying to type in complicated things like this. All right, let's take a look at one more and see what it's asking us to do. Okay, so this problem says we want to find A1. Oh, wow, so we want to find A1, but notice it says S. So we're going to start by just writing that S formula down. S of n is equal to A1 times 1 minus r to the n over 1 minus r. And let's just start plugging in what we know. It tells us that we have S of 8. Right, so it says, hey, use S of 8 to find A1. They even told us R, right? So we know what R is, 1 minus 3. We know this n as well, right? Because the n is the same n as here, so this is to the 8th power. And on the bottom, we have 1 minus 3. And so the last thing to remember, and this is kind of key, is to remember that, when you're doing this, this number goes here, right? So we're going to put 6,560 here, and that's going to equal A1 times this thing. Now, one thing that students have a lot of trouble understanding, they understand that they're trying to solve, okay? But when they look at this very large amount of numbers and they think about the order of operations, they sort of don't know what they have at this point because there's so much on the paper. Now, what you actually want to do is you want to simplify this. You just want to type that into your calculator, because if I know what that is, I'm at the multiplication step, right? A1 times this mess. So let's figure out what that mess is, okay? So I'm just going to type in, 1 minus 3 to the 8th power. I'm going to highlight the whole thing, hit division, and type in 1 minus 3, or negative 2, and that's 3,280. So now that I know that, this is 3,280. Once I know what that is, there's actually only one thing to do, which is to divide by that, because again, I'm solving for A1. So all I have to do is divide by 3,280 on both sides. And let's see what we get, right? Because that's the only step we have to worry about once we figure out what this mess is. All right, so back to the calculator one more time. And let's see, we have 6,560 divided by 3,280, and it comes out to 2. So all that work, and we got that A1 is 2. Now, A1 does not have to be an integer. It can be a decimal or a fraction. The only thing it has to be an integer is this n value, which they gave us. So just using that formula like we did earlier, but in this case, using the formula to find different things. In this case, we found the first term using the series formula. And this one, we had to use a series formula, but we're missing information. So it can all be done. Just don't forget about your sequence equation formula, which sometimes comes in as well. So in this video, we're going to take a look at infinite geometric series, and you can see the little infinite sign in the formula. And what this is going to really do is talk about, again, the concept that we learned called convergent. Now, convergent really means that the series is collapsing or decaying, using the exponential terminology, down to adding eventually nothing. So let me explain what we mean there. If I start with 1 and my R value is a half, my next term will be a half. If I multiply this by a half, I would get a fourth. If I multiply that by a fourth, I would get a 16th. And if I just keep going, you can tell that the numbers are getting smaller. And in fact, they eventually, if I look at them as a decimal, they eventually get so small that they become trivial, right? If I just keep going here, they just keep getting smaller and smaller and smaller. And what that means is that eventually, when we keep going down to here, we're actually going to get to 0, because we're actually going to eventually have 1 over infinity, and that's where the infinity is here. If I went to the infinity term, if I went to term number infinity, then in this case I would have 1 over infinity, and 1 over infinity is called 0. Now that's your first time maybe you've seen something called a limit, and you'll see limits more when you are in calculus and pre-calculus. You might have thought about an asymptote, specifically a horizontal asymptote, as a limit, possibly when you did rational functions. So this actually makes this formula the same as this formula right here, the one we've been using, 1 minus r to the n over 1 minus r. What happens is, as r, as we keep going, as n goes to infinity, then this part right here goes to 0, leaving us with 1 over r minus n times a1, which gives us this formula. So just remember that when you're looking at this formula, really looking at this one. We do this when we have a convergent r value that's between 0 and 1, meaning a fraction or decimal that's between 0 and 1. The absolute value is to take care of if you have a negative r value. Even if these alternated from positive to negative, they eventually would still have the same problem. So keep that in mind, that they would eventually do the same thing. The formula would evaluate a different number with a negative in it, but it still would be useful. Keep in mind there's a hidden parentheses around the numerator and denominator. And very important is keep in mind that r value has a parentheses as well, because all these r values are going to be fractions or decimals between 0 and 1. So that extra parentheses is super important. All right, so let's take a look at some problems that we've seen similar to ones that we've already done, but that have notable differences. So the first thing you'll hopefully notice in this problem is that we have a fraction. We're going to determine exactly what that is. We also have this dot, dot, dot right here, and that is meaning that it's going to go on to infinity, right? It's going to infinity, which is kind of a key way to know what we're looking at. So nothing else changes. We're still going to find our R value by doing A2 divided by A1, which in this case would be 9 over 12. Please take super care that you're not doing this the wrong way. It's always the second one divided by the first one, because if your fraction's upside down, you won't think it's convergent. So here we get 3/4, and 3/4 is, it meets this requirement that the absolute value of R is between 0 and 1. So this is a convergent R value, which is required, okay, to use the formula. And then once you know that, you just use this formula, but only if it goes to infinity. I mean, if it gave us a term over here, if it gave us something, we would have to use the Sn finite. It's only when you have a dot, dot, dot with a convergent that you would then use this special formula for convergent infinite series. So our A1 value is still 12, just like it was before. We now have 1 minus R, which is 3/4, and then we just evaluate this using arithmetic. So on the bottom, we would have this 1, you'd want to change that to 4 over 4, and so you would get 1/4. And then you would use keep, change, flip, otherwise known as reciprocate your denominator and multiply it times your numerator. And so this will come out to 48. Okay, so I went ahead and evaluated it, I guess, to show you how that formula works. But it did ask me to write, that in sigma notation. So I'll change the color on that to match that font. That was the second part there. So what we're going to do now is we can go ahead and evaluate the sigma notation. We have everything we need on our paper. So it did say rewrite the following using the series sigma notation. We have our first term, so n equals 1. We're going to infinity. Inside here, we always just write the formula for the sequence, right, which is easier for geometric. And it doesn't change this at all. This doesn't change when I have an infinity. So A1 would be 12, and R we found to be 3/4. We're still going to have our n minus 1, which is what we want, and we found that this comes out to 48. So no matter how many terms we add, if we go to infinity, if we add a billion terms, it's going to be approximately 48. But if we add infinity, it'll be exactly 48. All right, so now we're going to take a look at some that are already in this notation. And when you have one that's complete like this, you have the infinity. Again, we're looking at this thing now. We have a 1, right? We have R. We're pretty much good to go. In this case, we're just going to be using the formula S infinity is equal to A1 over 1 minus R. And it's just a simple exercise of plugging the correct numbers in the right spots at this point. Please keep in mind to put that in a parentheses, and just remember that when we evaluate this, all you really have to do is just make this 1 become a number out of the correct denominator. 5 over 5 is 1. It matches that denominator. So now we end up with 2 divided by 1/5. And if you keep, change, flip, or reciprocate your denominator, however you were taught to do that, this would come out to 2 times 5 over 1. So this will come out to 10, meaning this thing is equal to exactly 10 with the infinity sign on it. So then we come to our second problem, which is a problem. It's actually exactly the same. You go back and look at the video we did here. It's exactly the same as this problem, but this one was to 12. And remember when we had this problem, we had to rewrite it because we didn't know the correct first term. And both formulas, both the infinity and the finite, have an A1 in them. So we have the same problem here. What we have is that we have a problem that goes to infinity, okay? But the problem is that this A1 can't be correct. And the reason it can't be correct is because we have a problematic exponent and we have a problematic start point. So the reason that this isn't such an important thing to look at is when I think about this formula, S infinity is equal to A1 over 1 minus R. The A1 is talking about an A1 that starts at 1 and has the correct exponent, which I do not have. So I'm going to do a little iteration here. I'm going to find A1, A2, and A3 using this formula. You may, of course, use a calculator if you need to. So what we'll do is we'll type in 6 and then 1/3, and then we'll raise that to, and if you want to, you can actually raise it to the 1 plus 2, so you can see exactly what you're getting. Just make sure it's, see, right now it's not an exponent. Make sure you make it an exponent. And so that comes out to 2/9, just like the previous one we had. And the nice thing about something like Desmos is you could just copy that and then just hit enter and do the next one and do the next one and just change it from 1. We're going to look at term 2 and term 3 and just toggle them. So those are your 3 terms. So 2/9, 2/27, and 2/81. And here's the thing, you don't have to write out 3. I just find that students understand it better if they have 3 terms rather than just 2. You really only need to find A1. And the reason is that I'm still multiplying, right, by 1/3 to get to the next term. And so the whole reason I make students write out 3 terms is so they can see what's happening. All you really need to do is just rewrite this formula. If you do this enough, you realize that all you really need to do is find A1, right? You just really need to rewrite A1 and the exponent. So this equation that we had up here is really n equals 1 to infinity. A1 was supposed to be 2/9 if I use the correct n minus 1 exponent, but r doesn't change. So to prove that to you, look, this is what we just had. I'm going to type in the new formula, which is 2/9 to the, oopsie, be careful with how you type. So click and then type in 1/3 and then raise that to the n minus 1. So if I want to do 1 there, I'd have 1 minus 1, right? So 1 minus 1, making that an exponent. And look, I get 2/9 again. And I can just take that again and I can just, iterate it 2 more times for you. Term 2 would be 2/27, and term, oops, sometimes you got to be careful how you write the stuff in here. So 2, and then I'll put a 3 there. There we go. So you can see that I'm producing the exact same terms. I'm just producing them with a equation that can actually be put into the formula. So now that I've rewritten with the correct A1, to find the summation to infinity, it would be 2/9, the correct A1, not the wrong A1, divided by 1 minus 1/3. Same deal here. This always happens because you're subtracting from 1, so we just change this to the correct fraction with the correct denominator to match the r value. And so we would get 2/9 divided by 3/3 minus 1/3 is 2/3. And then if you keep, change, flip, you can figure that out. Keep, change, flip, or multiply by the reciprocal. So 2/9 times 3/2 comes out to 3/9, which is 1/3. And of course, you could use the calculator for that, but it's not a bad idea to use your arithmetic. So this original problem is equal to 1/3. I just can't use the formula. And then this problem right here is also equal to 1/3. So this sort of throws students off, but you have to understand the formula requires the correct A1 balanced with the correct exponent and starting place, and that's why we have to rewrite it and figure out the right equation. All right, let's look at one that has to do with given information, finding whatever term they particularly ask for. And so this last one, again, we are kind of taught right here that, hey, this is an infinity problem. So we know what we're looking at. So as soon as you see that, your brain just needs to shift, right? It needs to shift to thinking about this formula. I see that, I write, oh, S infinity is equal to A1 over 1 minus R. And then I just see what I have. Well, S infinity is given, it's 12, meaning they did a problem like I did here, and I got 10 for this thing, and they got 12. A1 is what I'm looking for, right? So A1 in this problem is the actual question. Find A1. And then I'm going to divide that by 1 minus R, which they gave me is 1/3 right there. So same old trick here. I'm going to change this into 3/3. All right, so I get 12 is equal to A1 over 3/3 minus 1/3, which is 2/3. And a lot of students will get confused by this, and there's two ways you can do it, right? The first way you can do it is to just simply multiply by that on both sides, multiply 2/3 on both sides. The other way to do it, if that's confusing, is to keep change flip this, right? That's fine if you want, and so that would give you 12 is equal to A1 times 3/2, and that's fine, right? But then you would have to multiply by the reciprocal, which would be 2/3. So probably the best thing to do when you see a fraction, right, is to always just remember whatever the denominator is, 2/3, x, 17, just multiply by that denominator and it will always cancel. Just make sure you do the same thing over here. All right, and so evidently when you do this, A1 would be 2 times 12 is 24. 24 divided by 3 is 8. So evidently, it's not so bad to do. You just have to make sure you're following the right equation based on whether it says infinity or not. Now, keep in mind that problem, if I went back and looked here, it's actually almost exactly the same as this one. The difference is here I have an 8. 8 is a finite number, so I used S of n. Here, it said infinity, so I used the infinity formula. And then you just follow the solving techniques from there. But make sure you simplify before you try to solve. This is where I solved. This was just simplifying the denominator. Just don't forget about that parentheses, right, that we have here and here. That's what will help you get to this answer.